Hello everyone, I am Dr. Pallavi Deshpande and I would be teaching you the subject Electronic Devices and Circuits during this semester. Students, this is the core subject for Electronics and Telecommunication branch. In this subject, you will be studying various electronic components, their working principles, their characteristics, and their different applications. We have already discussed the syllabus of EDC during your induction program. And now, without wasting much time, I will be starting with our unit number 1. So your unit number 1 is diode circuit and applications. This is the outline for your unit. Semiconductor physics, diode construction and operation, voltage current characteristics of diode, diode models, half-wave rectifiers, full-wave rectifiers, power supply filters, Zener diodes, and LED and photodiodes. Student, as I told you, we are going to study various electronic components in this particular subject. So we know that most of the electronic components, they are manufactured using semiconductor materials. And we know 3 different semiconductor materials: silicon, germanium, and gallium arsenide. So before we start with actual PN junction diode, let us revise our concept regarding semiconductor physics. And then immediately we will go for PN junction diode. In this slide, I have shown you one atom of silicon. We know that atomic number of silicon is 14. In the nucleus, there are 14 protons and 14 electrons. They are revolving around the nucleus. And that's why any atom is electrically neutral. If you see its outermost orbit, then its outermost orbit consists of 4 valence electrons. Let us see another semiconductor material, which is germanium. Here also, its outermost orbit consists of 4 valence electrons. Now, student, if you consider the crystal of silicon semiconductor, then the structure will be something like this. Here, every 4 electrons which are present in the outermost orbit of silicon will make a covalent bonds with another silicon atom. And in this way, this particular crystal will be very, very stable. Okay. Same is true for GaAs also. See here, for gallium arsenide also. If you see the atomic structure of gallium arsenide in very first slide I have shown here. For gallium, there are 3 valence electrons present in the outermost orbit, whereas for arsenic, 5 valence electrons are present in the outermost orbit. So whenever we are using GaAs material, these 3 electrons will make a covalence bond with all these 5 electrons. Okay, so you get the most stable structure of that GaAs crystal. Now, basically, why we are using only semiconductors for the manufacturing of different components. So if you see, there are 3 different types of materials. One is insulator, another is semiconductor, and the third one is conductor. If you see the energy level diagrams for insulator, then this is the valence band, and here there is conduction band. A gap between the conduction band and valence band is known as energy gap, denoted by Eg. And see this gap carefully. This gap is too large. It is more than 5 electron volt. Whereas if you see conductor, then in this conductor, this conduction band and valence band, they are overlapping each other. So in the conductor structure, see here, the electrons which are present in the valence band, they are also available in the conduction band. those electrons are freely available for conduction. And hence, a material like copper, silver, aluminium, they are the very good conductors of electricity. Whereas in the case of insulator, even though you apply some energy, even though you bias this insulator, the electrons which are present in the valence band, they will not able to reach, they will not able to go in the conduction band because of the very, very huge energy gap. Okay. And whereas if you consider semiconductor materials, then there is a moderate energy gap between valence band and conduction band. If you see this energy gap, e.g., for germanium material, for germanium semiconductor, it is 0.67 electron volt. For silicon, it is 1.1 electron volt, whereas for gallium arsenide, it is 1.43 electron volt. So at room temperature, this gap, this energy gap is present. If you bias this particular semiconductor, biasing means what? We are applying energy to these electrons. If you forward bias, if you give some energy, some biasing to the semiconductor, then the electrons which are present in the valence band, they will get sufficient energy to move to conduction band. Once they enter in the conduction band, they are available for conduction. If you remove that bias, if you remove the applied bias, again, those electrons will come back to valence band. In short, what I want to tell you, in short, you can make on and off this particular material. That means the conduction and non-conduction of the semiconductor material can be controlled. It is in our hand. If we give bias, you will get electrons in the conduction band. If you remove bias, those electrons will come back to the valence band. And this is what we want. The on and off control should be in our hand. Then only we can use that material for the manufacturing of the electronic component. Whereas in conductor, such a control is not there. Okay. Similarly, in the case of insulator, what are the examples of insulator? Wood, glass, Teflon. These are the examples of insulator. Here also, we cannot make this material on and off. We don't have any control over those valence electrons. Whereas here in semiconductor material, we have that control. And that's why, student, most of the electronic components, they are manufactured using germanium or silicon or GaAs semiconductor materials. Now, keeping this thing in mind, let us see what is the meaning of intrinsic semiconductor and extrinsic semiconductor. Student, whenever I'm talking about a purest form of semiconductor, see here, if you see this structure, all silicon atoms are present. For every atom, there are 4 outer electrons present in the outermost orbit, and they are making covalent bonds with other 4 electrons. So it is the purest form of semiconductor. All silicon atoms are there. If I add some impurity in the semiconductor, then it will become extrinsic semiconductor. Okay. So let us see what is N-type and what is P-type of semiconductor. N-type and P-type semiconductor means a semiconductor having some impurity. That impurity may be pentavalent impurity or it may be a trivalent impurity. Now, if you see this particular diagram, here 4 silicon atoms are shown and 1 atom is shown which is antimony. Antimony is having, it is a pentavalent impurity. The meaning of pentavalent impurity means there are 5 valence electrons present in the outermost orbit of the atom. Okay. What are the other examples? Arsenic, phosphorus, bismuth, and antimony. All these are the different examples for N-type or pentavalent impurity. If you add these materials in the intrinsic semiconductor, then you will get extrinsic semiconductor, and that process is known as doping process. So in short, here silicon semiconductor is doped with a pentavalent impurity. So all out of 5 electrons, all 4 electrons, they will make covalent bonds with other 4 silicon atoms, but there will be 1 electron in excess, and that electron is nothing but a free electron. It is free for conduction. Okay. Now, for p-type semiconductor, the same thing. Here, a trivalent impurity like boron, indium, aluminium, or gallium, they are doped with intrinsic semiconductor. Okay. So here I have shown 4 silicon atoms and only 1 atom of boron. Trivalent means there will be only 3 valence electrons in the outermost orbit. So see here the outermost orbit is shown, and there are only 3 valence electrons, and there is one hole. Hole indicates there is a deficiency of electrons. It is waiting for electron. Okay. So such a p-type and n-type semiconductors, those are known as doped semiconductors, or in extrinsic form of semiconductors. Student, this is about the semiconductor physics. Now, keeping all those things in mind, let us go for PN junction diode. This is our first very basic electronic component. See here, as shown in figure here, one p-type and another n-type. These 2 materials, they are sandwiched together. Okay, so here a semiconductor material, but it is p-type and it is n-typely doped semiconductor material. They are sandwiched together, and this is a junction. This is known as PN junction. Now, as shown in the diagram, in P region, there are excess of holes, whereas in N region, there are excess of electrons. Or we can say here, electrons are the majority carriers, whereas here, the holes are the majority carriers. If you see these regions carefully, then not only holes, but few electrons are also present. And that is nothing but those electrons, they are known as minority carrier electrons here. Similarly, in N region, few holes are also present. Now, whenever such a region is formed, then immediately the electrons from N region, they try to diffuse in the P region. Okay, and they try to recombine with the holes. The same thing is shown here in the second diagram. Now see this diagram. Electrons from N region, they have diffused in the P region, keeping behind one positive charge. As that electron is entering in the P region, here you are getting the negative charge. The negative charge is left in P region. And student, this particular region, it is known as depletion region. It is depleted with all mobile carriers. So here only positive ions are shown, and here only negative ions are shown. Are you getting this? This depletion region, the name indicates it is depleted with all mobile charges. I mean, there are no holes and there are no electrons present in that particular region. Now, here you get some potential which is known as barrier potential. Okay. Now, see here. The same diode is shown here, PN junction diode. There is a small depletion region. A diode is nothing but basically a two-terminal semiconductor device made from either silicon or germanium. Okay, so two terminal. The terminal which is connected to P region, it is known as anode, and the terminal which is connected to N region, it is known as cathode. And this is the symbol of a diode. One small triangle along with this ring is a symbol of diode. Now, student, these are the different types of diodes. Here, this is the symbol of diode, and different types of diodes are shown in this slide. Gun diode, LED, that is light emitting diode, pin diode, then step recovery diode, laser diode, photodiode, character diode, Schottky diode, and so on. So these are the different types of diodes. Before we go to these different types of diodes, you should know basically what is diode and how it works. So let us see how to forward bias or how to reverse bias a particular diode. Student, as shown in the diagram, see here, this is PN junction diode and a forward bias is given. Forward bias means what? A voltage supply is connected in such a way that this positive terminal of a battery is connected to P type of material and negative terminal of a battery is connected to the N type of material. Okay, here one resistor is included. This is known as current limiting resistance. This is required in the circuit to control the current which is flowing through the circuit. Okay. Now, because of this bias, this particular diode has become forward bias. Now, we know that there are holes, or holes are the majority carriers in P type of region and electrons are the majority carriers in N type of region. Now, as I am connecting positive potential to holes, and holes, they are also having positive in charge. So what will happen? They will be repelled, these holes will be repelled from this terminal. Similarly, the electrons will get repelled from negative terminal. And what will happen? The electrons will enter in the P region and holes will enter in the N region. The same thing is shown here. See, basically student, there is a movement of electron. The electron will recombine with the hole and they will move from one hole to another hole, from this hole to next hole. And it will appear that the holes are moving, but actually the conventional current direction is the direction shown by flow of electron. Now, when this flow is possible, whenever you are applying V bias, which is greater than this barrier potential, the barrier potential which is present here at the junction. So what is condition for forward biasing? Your biasing voltage should be greater than the barrier potential, then only the actual current, there will be only the movement of electron in this particular circuit. So have you understood about forward bias? Okay, now let us see how to reverse bias a diode. Okay, before going to reverse biasing, let us see what is the effect of forward biasing on depletion region. Student, as I am forward biasing this particular diode, what will happen? The holes from P region will be pushed in the N region and the electrons from N region, they will be pushed to the P region. So obviously, it will reduce your depletion region. So this is the depletion region. Just see here, the figure shows a reduced depletion region with forward biasing. Positive terminal, the anode is given with positive potential and the cathode is connected to negative terminal. Is that clear? Now, let us see how to reverse bias a diode. Here, exactly opposite biasing you have to provide. The same PN junction is shown. This is the junction, and I'm applying here negative voltage to now P region and positive voltage terminal to N region. Okay. So what will happen? The holes which are present here, which are the majority carriers here, those will be attracted towards the negative terminal. Whereas electrons which are negative majority carriers here, those will be attracted towards this positive terminal. Obviously, it will increase the width of the depletion region. So the same thing is shown here in this particular diagram. Just see here, the width of the depletion region is increased because most of the holes, they are attracted towards this particular negative voltage, and electrons, they are attracted towards the positive voltage. Okay. Still, in this reverse bias condition, you will get a very, very small leakage current, and that is because of the minority carriers which are present in P type and N type of region. So, for in P region, we know that the minority carriers are electrons, and in N region, the minority carriers are holes. So, because of those minority carriers, you will get a slight flow of current, reverse current, in this reverse bias condition. The same thing is shown here. Okay, because the minority carriers, they contribute in the reverse current. Now, student, whenever there is increase in the temperature, more and more electron hole pair will be generated. So what will happen? Whenever there is increase in the temperature, you will get slight increase in this reverse current because more and more minority carriers will be available during reverse bias condition. Okay. So definitely it is temperature dependent also. So reverse current as well as forward current, both currents, they are temperature dependent because in semiconductor, we are getting currents because of majority carriers as well as because of minority carriers. Yeah. Now, what is reverse breakdown? I will explain you this particular reverse breakdown from its characteristics. See here. 1 minute. Yeah. This is the diagram shows the VI characteristics curve for a diode. This is the forward bias characteristics and this is the reverse bias characteristics. Now, if you see the reverse bias characteristics, then even though you are increasing voltage from 0 to VBR, what is VBR? Reverse breakdown voltage. Up to this point, just see here, the current will be almost 0 because it is because of minority carrier. This current is because of leakage current. So it is very, very minimum current. It is approximate, it is nearer to 0. But whenever this reverse voltage reaches to breakdown level, then what will happen? The reverse breakdown will take place. The avalanche breakdown of a diode will take place. And because of that avalanche breakdown, your reverse current will increase immediately, suddenly. There will be sudden increase in the reverse current. So what is happening in that avalanche breakdown? See here, we know that we are getting reverse current because of minority carriers. And whenever I am increasing reverse bias, the voltage across this depletion region is increasing. You are getting more and more electrical charge present at the depletion region. And because of this very heavy electrical charge or potential at the depletion region, the minority carriers which are moving, those they get accelerated. And because of their acceleration, those minority electrons, they will knock out few electrons from the other covalent bonds. So what will happen? More and more electrons will be present in the circuit. Are you getting this? As I'm applying a larger reverse bias voltage, as I'm increasing reverse bias voltage, there will be more potential across this depletion region. Reverse current is flowing because of minority carriers. Those minority carriers are get accelerated. They get accelerated. And those accelerated electrons, they will collide with covalent bonds and they will knock out electrons from the covalent bonds. And there will be sudden increase in the number of electrons and you will get increase in the reverse bias current. Student, this particular condition should be strictly avoided in a regular diode. Okay, because it is going to damage our diode. So one should apply reverse bias voltage only up to this particular point. Below this knee point, below this breakdown point. Only here, only in this region, one should operate our diode. Is that clear? Now, let us see now the forward characteristics of diode. Student, here on x-axis, there is voltage, on y-axis, there is current, forward voltage, forward current I have shown. If you go on increasing forward bias, then after 0.7 volt in silicon, this is known as cut-in voltage. This is known as cut-in voltage. After 0.7 volt, you will get sudden increase in the forward current. Okay, so this particular voltage is also known as knee point. It is also known as knee point. Whenever your forward voltage is below this knee point, you will get very small amount of forward current. But as soon as your forward voltage goes above this point, then suddenly there will be increase in the forward current. This particular diagram shows dynamic or AC resistance, forward resistance of a diode. Here I have shown the expanded curve in which it is very, very clear. See here, on y-axis there is current, on x-axis there is voltage. So if I take delta VF, a particular duration, from this duration to this duration, and corresponding delta IF if I consider, and if I take the ratio voltage upon current, then you will get resistance. Now why it is called as dynamic resistance or AC resistance? Because this resistance is not remaining constant throughout the characteristics. It is not constant. It is changing. Okay, and that's why it is known as dynamic or AC resistance. If you see this curve, see particular this point here, for a little change in forward voltage, there is a drastic change in the forward current. Okay, so definitely here, as you go in this direction, what is happening? Your resistance value is reducing. Are you getting this? See here. For a small change in voltage, you are getting larger change in current. Larger change in current means what? Your denominator is more than numerator. So what will happen? Your resistance will obviously reduce. It is not constant throughout. It is changing throughout. Okay, and that's why it is known as dynamic or AC resistance. This reverse bias characteristics we have already seen. On x-axis, reverse voltage is taken. On y-axis, reverse current is taken. And as I told you, you must apply reverse voltage between this particular range. You should not apply it above the breakdown voltage. Here, the avalanche breakdown of a diode will take place, and this is undesirable. This should be strictly avoided. This is a complete VI characteristics for diode. Okay. Now, student, let us stop here, and I will send you one more audio clip on next topic. Thank you. Thank you very much.